Okay, so this is lecture 27. This begins module 4. So we're going to be talking about continuous time Markov chains. In module 4, we're going to learn how to model with continuous time Markov chains and some of the basic characteristics of continuous time Markov chains. Okay, so what we're going to do is we're going to start off in this lecture just an introduction to continuous time Markov chains and how they relate to what you already know. So recall with discrete time Markov chains, and basically a discrete time Markov chain was some kind of discrete time stochastic processes which you had this stepping variable n went from 0, 1, 2, so you can think about your time, went in increments of 0, 1, 2, etc., and your state space were integers. And then we say it was a discrete time Markov chain if you had these integers n, and you also had this Markov property, which basically was this memoryless property. So recall what we had here was that in the next time step, n plus 1, we're going to be in state j. Given that we've been all these places, it really only depends upon the present state. So the future is independent of the past, it only depends upon where you are at present. Okay, so some of the differences between discrete time Markov chain and continuous time Markov chain, well, the main difference is in the name, discrete time versus continuous time. So in discrete time Markov chain, we assume that we remained in a state exactly 1 unit at a time before making a transition. So in thinking back to some of the examples, when we thought about buying different brands of ice cream, for instance, we thought about every month people would either keep that same brand of ice cream or change to a different brand of ice cream. So it was monthly. Or for instance, like, what kind would you drink, coffee or tea on a given day? And so there we had a discrete time interval which was considered day. Or whether or not you would buy this lunch or that lunch on a given day. So you can think about time intervals being months, days, years, etc. So here we had, but the important thing is that it was discrete time. So you knew that you had exactly 1 unit at a time between this occurrence and that occurrence, and you were going to stay there. Now, it also means you can go back to the same state you were in. So like, for instance, there was a certain probability that if you bought brand A, you would stay with brand A. So it's just saying that here, the time in which there is going to be a change, if there is a change, is exactly 1 unit. And the unit is always fixed. So a continuous time Markov chain relaxes this restriction by allowing the chain to spend a continuous amount of time in any state. So a change can actually occur at different times. It doesn't have to occur in 1 month or 1 day or 1 year. So it's a continuous amount of time. The nice thing is that it still satisfies the Markov property. So it still has the memoryless property in the fact that the future is independent of the past and only depends upon the present, what's happening now. Okay, so let's assume that we have a state space that is our integers or some subset of the integers. And suppose that whenever a chain enters a state I, again independent of the past, then the length of time spent in state I is continuous. So we basically think about the length of time spent in state I as a random variable which we call Ti. This refers to what some people call as the holding time. So Ti is the holding time that is spent in state I, the length of time spent in state I. And again, this is a random variable, so we're going to have some kind of distribution. It's going to spend on average a certain amount of time in state I, but it's going to be distributed about that. So you're going to have some kind of mean, some kind of distribution. Okay, so the important thing here is that when the holding time ends, the process then makes a transition into another state j according to some probability, just like we had before. So we had the probability of moving from state I to state j is pji. We have the same idea here. It's just how long it spends in that state before it actually transitions. Okay, so let x of t denote the state at any time t. So again, we have a continuous time t greater than or equal to 0. It's a continuous time stochastic process with state space. We assume the future, x of s plus t, given whatever it is now, x of s, is independent of the past. So this is what we call a continuous time Markov chain. Okay, so the formal definition, so we always have to do the formal definition. The intuitive sense is that it can spend a random amount of time, and it has this memoryless property. Okay, so the formal definition is that a stochastic process with discrete state space S, so here we're still assuming that we have discrete state space S, is a continuous time Markov chain if for any I and j and s, and t and s that are positive or non-negative. Here basically what this says is that our state variable x at time s plus t, it goes to state j, given that it had all of this information before it. So it was in some state xu for all times between 0 and s. It's in state I at time s, and we're assuming it's going to transition to state j at time s plus t. So here we're saying that it doesn't matter what these previous times were, it only matters what the present time is, and we call this Pij, which now it depends upon time. So here's the probability that the chain will be in state j t units from now. So we still have our transition matrix P of t. However, now P of t depends upon time because at different times is more likely to transition or not, and P of 0 is still the identity matrix. So here, if we truly assume that that the future state doesn't depend upon the time, but it only depends upon where we're at. So it only depends upon state I here. It doesn't actually depend upon what S is. It only depends upon state I and how much time has gone by. So here what we can say is that S really doesn't matter here. What matters is the fact that our state is in state I. It's going to transition to state J after t units of time. So we really can think about this as at some initial time we're in state I. After t units of time we transition to state J. So the S really doesn't play a part here, so we can really just ignore that. And think about our new state, whatever state we're in, as our initial state. Okay, so our holding time for these properties, remember our holding time was the time that we stay in state I, has to be memoryless also. Okay, so in other words, basically what we have to say is that the probability that our holding time is greater than something here, given that we know some information about how long we've been in there, doesn't matter about how long we've been in there. So basically, however long we've been in there in a certain state doesn't make a difference. It has to be memoryless. Okay, so proof by contradiction. Suppose it is time S and you're in state I, and the holding time, how long you've been in there, really does make a difference. So in other words, the amount of time you've already been in state I is relevant in predicting how long you're going to stay there. What this says is that for any time r less than s, whether or not you're in state I at time r is relevant in predicting whether you're going to be in state I or a different state j at some future time s plus t. So for any time less than s, you're saying that it matters whether or not you're in state I or in some other state, and that where you're at time r has some relevance on what state you're going to be in. So basically what that says is the probability that you're going to be in state j depends not only on the present, but it also depends on where you were at previously, whether you were in state I or whether you were in state, let's say, K. So this violates our Markov property. So basically it assumes that it does depend upon where we've been and not just the present state. So basically what we have is that having this Markov property for our state space means that we have to have this memoryless property also for our holding time. Okay, so the only distribution which satisfies a memoryless kind of distribution is the exponential distribution, so our holding times have to follow according to an exponential distribution. So for each state I and S, there's some rate AI, so that such that the chain entering state I remains there for any amount of time that depends upon this exponential, and it behaves according to an exponential distribution with rate AI. Okay, so just some of the basics. So I would advise you to look back at Module 2 for some of the basics. And we're also, in two more lectures, we're going to talk a little bit more about the exponential distribution. But one of the things that, when I introduced the exponential distribution, the expected value here of our holding time, expected value of any variable Ti that is exponentially distributed is 1 over the rate. So this is going to be important in some of your homework stuff, and we'll also be talking about it in 2 lectures when I do some examples. But just to remind you, the expected value, and here we assume that the probability of transitioning from state I to state I is 0 for I and S, then AI can be interpreted as the transition rate out of state I. So what's the rate that we would actually leave state I? So again, here the intuitive idea is that the holding time will end at some interval, let's say dt units of time, and the probability that it'll end is AI dt. Okay, so next time we're going to talk about the process, which is a specific type of continuous time Markov chain.